Hey team, welcome back. Today's video is about solving higher order differential equations using numerical integration. We've talked before about solving first order differential equations. So here's a first order differential equation. This notation with the dot, if you're not familiar with that, q dot is another way of writing d dt of q. Because we use derivatives with respect to time so often, we have a shorthand for it, which is simply a dot on top. If we wanted to use Euler's method to integrate this, we know that we need to define some function, f of y and t, and really this function is, it's a function for the derivative. So in this equation, what is the derivative equal to? Well, q dot is going to equal 1/2 5 minus 10q. And that's literally the solution, and you can take this, define it as the function, and then numerically integrate. So obviously we can do that. Let's modify this system, and let's add to it a q double dot. First of all, what is the order of this equation? Well, we can see there's a q double dot and a q dot. You don't add them. If you have the same variable, multiple derivatives of the same variable, all you look at is you look at the highest order derivative. So this is a second order. I'll write it down here. This is a second order differential equation. Now, when we perform numerical integration, you perform numerical integration on first order differential equations only. What that means is we need to take this second order differential equation and we actually need to turn it into two first order differential equations. So let's talk about how to do that. To convert this equation into two first order differential equations, we're going to use state variables. And all that means is we're going to convert this equation from q's into, usually we use x's for state variables. And we just have to find some way to recast the problem. Now, how many state variables do we need? Well, what was the order of the equation? Second. That means we need two state variables. So we need x1 and x2. So what are x1 and x2? Well, what's the variable in the equation? It's a q. So let's start with q. I'm going to say that x1 is equal to q. x2, well, we have q and then we have q dot and we have q double dot. So let's make x2 be q dot. Now, I said we're going to be solving differential equations, right? These are not differential equations for x. These are just equations for x. What we can define next then is we can define x dots. So let's say x1 dot, x2 dot. So what is x1 dot? Well, x1 is equal to q, so x1 dot should be q dot, right? But q dot is x2, so x1 dot is x2. And then what is x2 dot? Well, x2 was q dot, so x2 dot is q double dot. So what is q double dot? We actually have an equation for q double dot. That was our original differential equation. So I can say q double dot is equal to 5 minus 2. Now I don't want any q's in these differential equations. So it's 2 times q dot is x2. And then minus 10, and this is x1. Q is x1. Okay. These are first order differential equations, and I have 2 of them. So what you can do inside of your code is you can define a state vector. So let's say that x is the vector of state variables, and x dot is the vector of the derivatives of the state variables. Can we solve for x dot? Well, yeah, I have equations for it. I have an equation for x1 dot, and it's x2. I have an equation for x2 dot. There it is, and it's a function of x1 and x2. So how do we solve this then? Well, let's take Euler's method and let's just recast it using state variables. The update xn plus 1 is equal to the previous values xn plus delta t multiplied by x dot at time n. This was the equation that we had last time, Euler's method, and it worked for a single variable. Well, guess what? It also works for a whole vector of variables. Let's think about the dimensions in this. For the system we've done here, the dimensions of x are 2 by 1. Time is simply a scalar, and then the dimensions of x dot, well, these are 2 by 1 as well. And if you take a 2 by 1 and you add a 2 by 1, well, you get a 2 by 1. So in this process of doing it as a vector, we solve for what is effectively an acceleration. This acceleration updates the velocity. So when you integrate x2 dot, you get a change in x2. So the acceleration causes a change in the velocity. At the same time, x1 dot is the velocity. And when you integrate the velocity, you end up with changes in the position. So the solution to this system is the history, the trajectory of the x vector, which means at the end of this, you get the time history for both the position and the speed. And you found that by numerically integrating the acceleration. That's it for this video. I'm going to do a screen capture where I show some code for higher order systems. I'll see you next time.